Hello everyone, I am Stefano Di Gregorio. One of the key challenges in modern autonomous robotics is ensuring safe navigation in unknown environments. In my thesis, I addressed this problem by developing an algorithm that integrates learning techniques based on Gaussian processes with a control-theoretic safety framework grounded in control-barrier functions. While CBF methods offer strong theoretical safety guarantees, they face two main limitations in practice. First, their inherently one-step optimization often leads to myopic and suboptimal behavior over time. Second, the design of effective barrier functions a priori can be extremely challenging, especially when the environment is unknown or only partially observed. To overcome these limitations, in the thesis, the control barrier function is designed directly by conditioning a Gaussian process on sensor data collected online. This allows a non-parametric representation of the state constraints, allowing a scalable approach even when many obstacles are present in the environments. Also, by fine-tuning the hyperparameters of the GP, like its length scale and the kernel structure, a trade-off between the conservativeness and the flexibility of the CBF approach can be found. The algorithm follows a four-step workflow. First of all, data is collected from the robot sensors. Then, the Gaussian process is conditioned in order to obtain the posterior mean function. We have then the computation of the control barrier function and the control barrier certificates performed via Lie derivatives computation along the system dynamics, and finally the control is rectified using a quadratic program. In these figures, it's possible to observe how the safety function characterizes the surrounding environment when data from it is available. Notably, different Gaussian process kernels produce different behaviors. For instance, the top figures show the CBF and its derivative using a reciprocal kernel, while the bottom ones use an exponential kernel over the same environment. This illustrates how kernel choice and hyperparameter tuning can be used in order to adapt the safety behavior in real time, based also, eventually, on specific mission requirements. We then tested the algorithm in a navigation task where a unicycle robot moves towards a goal while avoiding static obstacles. Thanks to its fully online structure, where the Gaussian process is retrained from scratch at every control step, the algorithm demonstrates robustness even in dynamic environments, as shown in the simulation on the right, where the robot reacts to moving obstacles. Finally, the method was implemented in a ROS2-based framework and tested in a physics-based simulation to validate its practicality. Despite the online reconditioning of the GP at every step, the algorithm remains computationally tractable due to the small dataset size and the availability of a closed-form solution to the quadratic program.